Hey everyone, welcome to another one of Erik and mine deep dive into an Exercism exercise. And this week we're looking at reverse string. And this is a good one because not only does it deal with the exercise on Exercism, but we're also going to be looking at just 14 ways, I didn't know that many, 14 ways to reverse a string in general. So it's going to be a big tour through lots of things. We're starting off using some basic functions and methods. We then end up looking at graphemes and Unicode. We then end up moving towards looking at the heap versus the stack, of using pointers, all sorts of stuff. So it should be a fun tour. I know, Erik, you're excited for this one. So yeah, let's just dig straight in. So firstly, we have a solution from Kotlin. I guess this is the most basic, and maybe again we talked about this in the Leap video before, the most cheaty way. Erik, tell us what's happening here.
There's not much to say here. Reversing a string is so common that the vast majority of web frameworks will have, or languages will have something in their base library that just does it for you. Kotlin has that too. So there's an input string and you just call reversed, and that will return a new string with the reverse order. So very simple, very elegant. Nothing much to say here. Just it's built into the base library, and you can just use it.
Yeah, I guess the only thing slightly to be aware of here is whether your language or what your language's Unicode support is like, and we'll talk a bit more about this later, but what that reverse is doing, whether it's reversing sort of individual bytes or reversing Unicode Codepoints or graphemes. And as I say, we'll dig into all this, but even though there's that function there available for you, it's still worth making sure you read the docs on it and understand exactly what that's doing. And yeah, we'll get a bit more into that. And then I guess sort of the brother or the sister to that method is the function approach, which is what we're seeing here in Haskell, Erik.
Yeah. So you might think this is exactly the same thing, and it's almost. The thing that's different, though, is that reverse is not actually a function on strings. It's actually a function on lists. And in Haskell, a string is internally represented as a list of characters. So whereas in Kotlin, for example, it might be a list of characters under the hood, but you don't really see that. But in Haskell, it is actually just a regular list, but then of characters. So this means that everything that you can use with lists, you can also apply to strings. And that includes the reverse function. And you could even do some shenanigans with partial applications, just remove the str bits. So you would just have reverse string equals reverse. It would just be an alias for the reverse function, but that will work too because function definition would stay the same. But the key thing to note is that the internal representation in the language can definitely change. So in Kotlin, a string is not just a list of characters. So you can't just treat it as a regular list, even though many of the functions that work on collections also work on strings, but that's something that's built into the language. But this is just the way Haskell works. The string is a list of characters.
And that's, of course, not always the case. And if we look at this next solution, which is JQ, here you can't just call reverse on the string.
No, JQ strings and lists are different. So the value input parameter is a string, and reverse works on I think it's a list. So what you first do, you have to convert the string to a list. So you do that via explode. Then you can call the reverse function on it. So you get back a reverse list. And then you do implode again to convert it back to a string. So you can see here, this is like a functional pipeline. You start with a string, then you move to lists, then you reverse it, and then you move back to a string. And this is a pattern that you see in many other languages too. So usually reverse is defined for lists at least. It might not be for strings. And if that is the case, you do something like this, where you convert your string to a list first.
Okay, so those are the, I guess, the built-in functions, methods, and some of the differences of those. Next up, we get to some of the sort of more standard algorithms, I guess, that people use to actually solve this in a slightly more less cheaty way, should we say, but also probably a less production way. In production, you probably want to be using those ways we've just looked at. So first up, we have nim. Tell us what's happening here, Erik.
So here in line 2, we have a for loop for C in string. So this is just going over all the individual characters in the string. And what it would then do is assign to the result value. And result is something that's special in nim. Every function that returns a value has a result. In this case, we're returning string. So result will be initialized to a string value. So you don't have to allocate it yourself. You can already work with it. And basically what this does is will prepend the character to the string. So even though we are iterating over the characters in the string just regularly from left to right, in the end result, they will be added to the front. So if you do that regularly, the last character that you add will be the first in the result string. So this is a fairly nice way of still having like iteration from left to right, but the end result is still reversed.
Nice. Do you want to just tell us a little bit more about this result, I guess, variable? When's that initialized? Is that initialized as soon as you enter the function, or how does that work?
Yeah, when the function is called, and your functionality will be executed just before that, the result value will be initialized. In later nim versions, they are actually recommending that you do it explicitly. So at the start of the function. So there is a bit of a change in strategy there, where I don't think this is actually recommended anymore. But I still think it's a really nice thing. So you can still use/abuse it.
Yeah, that's cool. Okay, so then the next algorithmic approach we're looking at here is one for JavaScript.
Yeah, I think if you start out trying to come up with an algorithm where you have to do it yourself, you probably come up with something like this, where you are iterating over the source string, but you do that in reverse order. So we have a for loop, and we have the value that we started, it's called index, and that's the string length -1, and that's equal to the index of the last character. And then we keep on iterating over the index until it is less than 0, then we stop. So this is going backwards. So starting at the last index, then the next to last, etc., until we've reached the first, we process that, and then we stop. And then in each iteration of the loop, we append the value at that index to a string variable, which is called new string here. So you get back a reverse string. So this is going backwards. It's character by character, so you go from the last to the very first index.
So in the previous one we saw in nim, you're reading in the normal order, but then building the new string by putting it at the front each time. Here you're reading in reverse order, but then building a string in a more sort of normal way of putting it at the end each time.
The reason why people try and do this is usually because adding to the end of something is usually quicker. But it also does depend on the language and the data structures. But in many cases, you want to append to a string and not prepend.
Yeah. I guess as well, a lot of people might not be used to seeing for loops like this. I feel like for loops are so often just used in a sort of work through a list, just, add one to the index each time. That's 99% of the time. There might be people out there that have not written sort of for loops that go backwards like this, but it's nice to see. And I guess as we move on to look at Java, we see here it's starting to use a string builder, and I guess this is to do with sort of the mutability of strings. Do you want to talk a bit through what's happening here, and then about how that's different to JavaScript?
So the core logic is exactly the same here, where you have a decrementing for loop. We're starting at the last index, ending at the first. And only now we're not appending to a string value, but we're appending to a string builder. And as you probably can guess from the name, that's a type designed specifically to build a string. And what you mentioned is absolutely correct. This has to do with immutability. So immutability means that once a value has been created that's immutable, it can't change later on. And that holds for strings in many languages, including Java and including JavaScript. So when you create a string in Java, if you want to, add a character to it, you can do plus, but what you get back is a new string. Even if you do plus equals, so the JavaScript version we just had before did plus equals, so it looks as if you were actually adding a character to the string. Under the hood, what was actually happening was that it created a new string with the added character. So you would have two strings in memory. And you can see that if you have a very, very long input string, you would create, well, basically length number of string instances in memory, which is obviously bad for memory and thus also for performance because you have garbage collection. Java has this very same issues, hence the creation of the type called string builder. So what does that actually, how does that work? So what string builder will do, it will allocate a bunch of memory with some fixed value. I looked it up for .NET. I think the default value was 15 characters long. So it will allocate an array of characters of 15 long, but it will keep track of two things. So the length of the array and the number of characters in the string, which will initially be 0. But if we now do this for loop and we only, write 6 characters into it, we haven't exceeded the capacity. And then when we return the string builder.toString at the end, it will just use the memory that was allocated. Nothing, there won't be like 6 strings in memory. There will just be the one string builder with the capacity, not going over the capacity. So that will be very optimal. But if the string would get very long, so you would, you would write 30 characters, which exceeds the capacity. Internally, the string builder will see that and will allocate a new slab of memory of bigger size. So that would incur a performance hit, but it will be less so than allocating all these individual strings. So if it's really dynamic, and you have to benchmark this, because obviously there's also a downside to the string builder because, well, you are allocating memory that you might not need. So always be sure to actually benchmark this. But the general gist is that you save on allocating individual string instances.
And I know in a lot of languages as well, you can tell the string builder how big the string is likely to be. And then it will allocate the correct amount of memory up front. So you could probably do this telling the string builder, that its input string length would be set.
In this case, it probably should be.
Cool. So, yeah, exactly. So I guess this is just, if you're not used to using string builders, I remember when I first saw them, it just seemed like a pointless extra thing to have to learn and think about. But once you start building, more complex strings, if you're building, web pages where you're rendering out quite a lot of text, and you keep adding new bits onto that and appending things, definitely thinking about, using string builders. It's a really useful tool that you can have in your belt that you can be much more efficient and optimized and performant with when you're doing these things. So another sort of algorithmic approach, I guess, although it looks so simple at first glance that it almost doesn't look like an algorithm, is this Julia code, Erik. Do you want to explain what's happening here?
Yeah. So we're basically doing the reverse iteration, but then in a slice-ish, range-ish format. So if you do phrase, which is a string in this case, and we do the square brackets, that's a slice, or a view. Many languages have different names for it, but it's basically you grab a part of the string. Usually it's a substring, so you grab not the entire string, but in this case, what we're doing, we're saying, hey, the range is from the end, so that's the index of the last character, to the beginning, so that's the very first index, and then do -1. So you go backwards here, so the range is last one, next to last one, etc., until the very first one, and that is the entire slice that you return. So we're using slices and ranges in combination, and it's a very concise way to basically encode the reverse for loop that we saw before.
Okay, I think this is the last of the There's two more algorithmic ones that we're going to look at first. So this one, I think you told me before, this is like the classic algorithm. If you're doing a job interview, this is the one that they're looking for you to do.
Yeah. So it's a classic interview question where they're saying, if you have a string, how would you reverse it? And they are looking for a very optimal way of doing that. And probably the most used algorithm here is you're not doing reverse last index to first index or first index to last index, but you're actually going over half of them, because the idea is that you're doing an outside-in swapping. So you start with I equals 0. So you have the very first character, but if you do length -1 -0, you get the last character. And then what you can do is you can swap these. So the first character becomes the last one, and the last character becomes the first one. Then you increment the I, so you would have 1, and then you would have length -1 -1. So that's the first character and the next to last character. And then you swap these. And you do that until you reach the middle. And that's the benefit here is that you're only doing length divided by 2 iterations. So that's less than, doing length iterations. So this is more optimal. And usually in this algorithm, you would have to use a temporary value because, you have to store one of them. Then you assign the other, and then you can assign it back. But actually C++ has something built into it, which is called std : swap. But if you don't have that in many languages, you would just see a temporary value being used. But the key part is that you're doing less iterations.
Yeah. Having the built-in swap function as well makes a huge difference here for just how readable and nice this becomes. I guess as well, the other thing that was jumping out to me when I was looking at this was the fact that size divided by 2, I imagine, just is an integer that's flawed, that has everything after the decimal place taken off. So it doesn't try and reverse the middle one with itself. But I suppose it would work either way, thinking about it.
But I think it's flawed, yeah. If your language doesn't have swap, but it has tuples or tuples, we had that before the discussion. You can often do the same trick where you have on the right side you have the tuples in original order, and in the assignment you have them in reverse order. So that would actually sort of not have you use the intermediate value. So I've seen that trick used in a lot of languages too, but you have to have some sort of tuple support in your language for that to work.
Okay. Very cool. So if you're ever doing a job interview, this is the one to remember before you go in. We have a version now looking from Bruce's solution in 8th. This a first look. I'm guessing this is similar to the one we just saw, Erik, but this looks a little bit more esoteric. I don't immediately know what's going on here.
So if you have the interview question and you come up with this, I'm guessing that the interviewers will be very impressed. So 8 is actually a fourth dialect, and fourth is a stack-based language. And that means that when you do something, you work with things that are pushed on the stack and popped off the stack. So this is actually the same algorithm that we had before. It's just more concise. So if you look at line 2, you can see s:\length, and s is the input string. So what that will do is it will put the length of the input string on the stack. And then the second thing is the number 2. It will put that on the stack. So now we have the length of the string and 2. And then there will be the division and : /. So that will be the length divided by 2, and then the remainder. And I think the remainder is skipped, but this is the division that's being stored. So modulo, I think mod returns 2 values, the remainder and the div part, and nip just removes one of them. Yeah. So you get left with length divided by 2, basically. And then the third line.
Wow, that's a lot of code to say that.
Yeah, it's not that much code. So it's just that we're not used to.
Maybe not. It's a lot of parsing.
Yeah. And then you have the actual loop. So you see here again in a somewhat different format. You see the length being put there again, and then you have the the one minus. So you do the end thingy, and then you swap them. So you have the S colon and then the bracket thingies. I think that's the swap. But I am not well versed in 8th, so I am sorry, Bruce. But the general gist of it is that this is the same version being done in the C++ version, where you only iterate over things length divided by 2. So this is also very optimal and extremely concise.
Nice. So yeah, if an interviewer ever says you can use any language you want, you can show them you can do this, and then really either impress or confuse them. One of the two. They'll be secretly there in the background on ChatGPT, copying and pasting this in and trying to get ChatGPT to explain what's actually going on so they can look impressive in the interview. Okay, cool. So those are sort of the normal algorithmic ways, I guess. Next, we're moving into Zig. And yeah, this is okay. This sort of I see how this is working. Talk us through it, Erik.
Yeah, so we're not focusing as much on the algorithm here. We're more focused on the representation of the string. So in Zig, there is no, which is a fairly this is a systems language, so you can work with things in a very sort of low level, but also higher. Of course, I wouldn't want to have Zig be known as a very low level language, but you have a lot of direct access to memory contents to have it be incredibly fast. And one of the ways in which it does that is just, there is no string type. There is just slices of bytes. So you see here, buffer is the square brackets, that's a slice. And then you have U8, and U8 stands for an unsigned integer of length 8 bits. So that's just a single byte. So a string is just a collection of bytes. There is nothing here about, I don't know, Unicode stuff. We'll get to that in a second. There is just bytes. And that's also why Zig can be very, very fast. So, and then the actual iteration is for S. S is the input string. And then the 0 ... that will be, if you do in Ruby, if you do each with index. So you can get the actual index that's paired to the character in the string. So you see that between the vertical braces, the vertical bars, you see C, I, and C is the character and I is the corresponding index. So that will be C is the first character, I will be 0, and then the second was 1, etc. And then it's just so it's doing front to back, and it will assign them at the end. So length -1 minus I is starting with the last character, etc., etc. So the first will be the last, the second will be the second to last, etc., etc. So it's the one that we saw in NIM basically, but not with the prepending, but with the assigning by index.
And you might not know the answer to this, but has the buffer already been like initialized with a certain length, or is it effectively just like an infinite buffer that you can just be writing into?
I think it has been pre-allocated, yeah. So normally in NIM, everything that's being allocated is very, very explicit. There are no hidden allocations. That's one of the selling points of NIM. So if you would look at the corresponding test code, you would see an allocator being used to allocate the buffer to write to. But I think in this case, the buffer will have the right size already. So there won't be dynamic memory. It's just pre-allocated.
You said NIM, you mean
Zig,
Zig, right?
Sorry. Yeah.
That's right. Yeah. Too many languages.
I definitely meant NIM.
You definitely meant NIM or Zig?
I meant NIM when I was referring to the previous version, but this is Zig. So Zig is explicit about allocation.
The allocation.
Yeah.
Okay.
Sorry.
Good. It's all right. I just don't want to confuse people. Okay, so next up we have Go. And this is the first time we're, I guess, starting to think about Unicode explicitly.
Yeah.
And we've got runes here. Do you want to explain what runes are if people don't know?
Yeah. So Unicode is a specification for how to encode characters. And Unicode has a thing that's called Unicode Codepoints. And Codepoints are basically just numbers that are associated with a certain character. So there is a Unicode code point for an E or for a semicolon. So that's all very simple, and you have that in ASCII too. The thing that's different on Unicode is that there are a lot of characters that Unicode can implement. Basically, any character that you can ever think of, there will be a Unicode code point for that. But that's not just... so there are numbers, so you can encode Unicode code points as bytes. So you can just store them in a byte. And I think that's actually what Go also does. So Rune is actually a byte, but it is explicit about that it's not just a byte, it's a rune. So it's a Unicode code point. So instead of iterating over, I don't know, bytes or whatever, you are being now explicit that you are iterating over runes, even though I think it's internally still a byte. But we are in the Unicode domain now with Unicode terminology, etc.
So yeah, this is the same algorithm that we've seen, but rather than working on just a list of anything, we're starting to deliberately now be working on lists of Unicode code points, or in Go's terminology, runes.
Yeah, there are still issues with it, and we'll see that in the next how you can work around those. Okay. So Unicode is very interesting in that, for example, if you have an E with an accent, that's a character. So you have a Unicode code point for that. But you can also encode it as a regular E followed by the accent code point. And that's a grapheme, a Unicode code point cluster. So those two code points make a single rendered character. And that is called a grapheme. So if you see an E with an accent, there are actually multiple ways in which that could have been encoded. One of them is just the one character, so it will be one code point, but it could also have been two code points. So you can start to see why the previous versions might be wrong, where if you start with the accent character, when you are reversing it, so instead of E accent, you would have accent E, that will be weird because they would have to be in the right order, even though they are reversed. So you will get the wrong result if you would just do it byte by byte. Instead, what you actually would want to do is to treat that E accent bit as a single thing. And that's called a grapheme. And that's what we're doing here in Gleam. So you see here the input value string is converted to graphemes, then it's reversed, and then it's, because it's a list of graphemes, and then we reverse the grapheme, so you will still have the E and the accent as a single thing in the list, so it will still be the right character, and then you join it again to a string. So working on the grapheme level, that's actually sort of foolproof, because the things that go together are kept together. So you don't have the wrong order anymore of code points.
And so this is really where you need to be getting to in any language. And the question is, when you're doing a dot reverse, is that working on graphemes? Is that working on code points? Is that working just on bytes? And it's important to know in your language how strings are how strings are considered when you're calling these methods on them, or you're calling functions on strings. Certainly in Ruby, like until I started doing this exercise, I didn't actually know any of this in Ruby, and I just presumed that you could do string.reverse and other things. But actually, you do need to go and get the graphemes out and start working with those as well. So yeah, it's really interesting. And one of the things to be aware of as well is that all of these ideas around Unicode and graphene have developed over time. So if you went back, I guess even 20, 25 years ago, a lot of programs and therefore a lot of languages were still thinking in terms of ASCII. And it's only as we've sort of moved through the 21st century that we've started using Unicode so commonly and so normally, and that's become the new default to replace ASCII effectively.
Yeah. And we haven't even we haven't even touched upon UTF-8, UTF-16. So and those are ways to efficiently encode Unicode code points. So let's not go into that. But there's a great Joel Spolsky article, Everything You Need to Know About Unicode, I think. At least if you search for Spolsky and Unicode, you will get a lovely article. If you are interested in this, I think that's of the best resources that you can use.
Mm-hmm. Agree entirely. Cool. Anything else you want to say about any of this, Erik?
No, not really. Just want to say that you don't have to do it like that in Gleam. There's also a string.reverse, but I just use this for that education purposes.
Nice. Okay, so next we want to start thinking about efficiency and how to make this even more efficient. And the next bit of code, it's not actually a solution. This is just something you wrote up, Erik, as one of the approaches for this, known as the span approach. But yeah, tell us what's happening here. This is C#, right?
Yeah, this is C#. So we mentioned before that you don't want to allocate a lot of strings, and in C# strings are also immutable. So C# has the exact same problem as a JavaScript or a Java. So there is also actually the very same type name string builder is also available in C#, but there is still a downside to that, in that the memory is allocated on the heap. So you have heap allocated memory, which is you can have a ton of it. It's basically boundless, not entirely boundless, of course, but practically it's almost boundless. And then, but it's slowish. And you have the stack, and the stack is very, very fast. And the benefit of the stack is that once you're done with the stack just gets thrown away. So you don't have to do any garbage collection. And that is what is happening if you allocate on the heap. And the garbage collection is, well, it will be very fast. But if you do a lot of performance sensitive work, you just don't want to have the garbage collection do any work, because it will affect your performance. So wouldn't it be great if we could just allocate on the stack? And in C# you actually can. So there is a keyword called stack alloc, and it takes a length of things to allocate. And in this case, we're saying, well, allocate the length, the input string's length, number of characters on the stack, and we assign it to span of har. And that's a built-in type, and it can only work on the stack. You cannot work with spans outside of the stack. So there are limits to this approach, because the stack has a limited amount of memory, but it's actually not that bad. You can allocate fairly large strings. I think I tested this with 100,000 characters and it still worked. So, but be aware that you might get you might run out of stack space if you get very long strings. But if you know your strings are small-ish, then this is absolutely a ton faster than allocating on the heap. So we're allocating on the heap, and then we're basically doing one of the aforementioned for loops. So we could iterate back to front, front to back. It doesn't really matter. We're doing front to back and then assigning back to front. So the code there is not that interesting. It's about the allocating specifically on the stack. So all the allocations for the new string are done on the stack until we actually return the new string. So that is the heap allocation. So we still have one heap allocation, but everything before that is done on the stack. And I have a performance article that shows that this is actually the fastest way to do it. The other ones are fast too, but it's just interesting to know that if you work with things and you're allocating things, and strings are very, very often, at least in the .NET namespace, the primary reason why the garbage collector is doing stuff. So the biggest amounts of memory are usually allocated by strings in regular applications. So if you can optimize that a bit, go for it.
So yeah, I've just got this performance article open here. It's under, if you look at the C# exercise for reverse string and go to articles, you'll see it here on Exercism. But yeah, the span method is 4 times faster than the string builder on sort of
you can see
smaller
that
strings, and then
it's
still 3 to 4 times even on big.
So in that little benchmark, you see Gen 0, and Gen 0 means it's the garbage collector doing stuff. So it's shortly lived memory that's being garbage collected, and you can see allocated too. So span does not allocate. So an allocation means heap allocation. It does, of course, allocate on the stack, but it's sort of ignored. So even for very large strings,
in comparison to just reversing the array, which is like, another very optimized method, this is still twice as fast as that until you get up to 100,000 characters, and then they're basically identical in terms of speed. So that's really really interesting to see. I guess. I know these are still characters, aren't they? So these are, I guess, thinking back to the graphemes, would these be graphemes still that are being swapped around?
Yeah,
So this is still working.
Yeah. So these are UTF-8 grapheme classes, I think.
That's nice.
I'm almost positive.
Really cool. Well, there's a whole article on there's a whole article on this and on some other approaches in C# on the Dig Deeper page for the reverse string exercise. So make sure you go and check all those out. Lots of tracks have been implementing these articles and other, and approach documents as well. So when you solve it on a track, make sure you do go and look on these.
Absolutely.
We've got one more solution to look at, Erik, and this is where we're really getting into the weeds. It's another one by Bobberhop. We saw one of Bobberhop's with Go earlier. This one again took me a moment or two to look at to make sense of it all. But it's not as bad as it looks once you read it through. But yeah, do you want to talk us through top to bottom?
Yeah. Just talking through C is always fun. So one thing to note here again is that, like in Zig, there is no special string data type. So what C has is pointers to memory, and a string is just a pointer to char values. So the memory is interpreted as chars. So chars are just characters, so bytes basically. But there are downs. The obvious benefit is that it's very memory efficient. You just have the memory there laid out. It's all sequential, so access is very good. But how do we know that we are at the end of the string? Because in language like a C# or a Java, there will also be memory, of course, but the string, you can ask it for its length. And there will be a value in memory stored that has its length. And that makes sense because strings are immutable, so it won't never change. So that value can be very optimized. But you can ask it for its length. But how do you do that when you don't have that information, basically? Well, what C came up with is that there is a special character, a null terminated character, and that's basically saying, hey, this is the end of the string. So if you would have the string Jeremy, which is 6 characters, you would represent that in memory as 7 characters. So you would have Jeremy, and then you would have the null terminating character. And then when you would iterate over the memory, once you see that null terminating character, you know, oh, this is the end of the string. And that is what you can also see here. So the reverse string has a character pointer. The name is value. The first check is to check if it has a value. Otherwise, we return null. But if it has, we're calling the string function to get the length of the string. And that will do what I just described. Just iterate over the string until we get to the null terminating character. Maybe there's an optimal way of doing it, but that's the general gist of it. We have to use a function to get at the actual length of the string. Then we allocate memory with calloc, and we allocate memory of length equal to the length of this input string plus 1. And that plus 1 is very important because that's our null terminating character. We are saying that we store that in a reverse pointer. So this pointer, reverse, will initially point to the very beginning of the allocated memory. And that is important. In the for loop, the thing that we start out with, that's one of the tricks in this solution, is reversed plus equals length. So what that basically does, if you have that memory bit, so we will start at the beginning, plus equals length, we'll move it to the end of the string, so the last character. Then within the loop, the if condition is star value, and that's quite cryptic, but that's basically the value that the character, the byte, that the value pointer is pointing to. So Bob is abusing/using, depends on your perspective, using the fact that the null terminating character evaluates to false. So all the other characters will evaluate to true, but once the pointer points to the null terminating character, this will be false, and we will stop. So basically, you could also write this if star value equals to the null terminating character. That would be the same thing as this. This is just more concise. at the end of the for loop, we'll increment the value. And they're basically saying the pointer will point to the next item in memory. So it will be the next character. And then within the for loop's body, we assign the value where we're currently at with the input pointer, which is doing front to back, with reverse. And that's the other pointer. And we do the other pointer, we decrement. So it will be back to front. So we have 2 pointers. One is initially at the very first character of the input string. The other is reversed and it's pointing at the last character, actually the last +1 of the reverse string. And then it will do assignment until it's done. And that done is when it sees that the input pointer is pointing to the null terminated character. So
clever.
That's C.
Very clever. So effectively, all we're doing there is iterating through the string, and we've got another string. We've basically got 2 strings, and we're going duff 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 duff, something like that.
Yeah.
But with a lot of the manual under the hood stuff being shown. Is that fair?
Yeah. This is basically using pointer arithmetic to very efficiently do the last to first, next to last to the second, etc. bit. So, but with C with C functionality, and in part this is because you have to do things differently in C because strings are just character pointers to memory.
Mm-hmm. Super cool. That's the last of our solutions. Thank you, Erik, for putting that together. I hope that's been an interesting tour through the world of reverse strings. There's definitely, obviously, tons more to dig into about the Unicode stuff. There's a lot of manual memory stuff to think about. I do, as I've said, recommend looking at these different articles. They're in lots of tracks now, approaches and articles on the Dig Deeper page. So go and take a look at that. Thank you to everyone that's been contributing those articles and continues to do so as well. But I think there's a lot here that it's a very simple exercise, but there's a lot that you can start digging into and a lot you can learn and a lot of fun that you can have just playing with these different approaches and trying to work out why one is more efficient than the other. I also think really important to look at the languages you work with day to day and have a look at what their actual functions do, understand how they work with Unicode, understand what reverse is actually doing. If you've got an open source language, which nearly all of them are, it's always fun to go and actually just read the source code to your language and work out what the actual reverse function or method is doing under the hood as well. So highly recommend doing that. If you haven't yet solved this for 48 and 24, please go and do it if it's still in 2024 while you're watching this. There are 3 featured tracks. Erik, can you remind me what the 3 featured tracks are for this?
I have to look it up, but I'll get to that in a second.
Somebody did ask me after the Leap video to highlight what the featured tracks are, and I've forgotten to write them down, but we will find that out. But yeah, one other thing to say as well, if you're doing 48 and 24, a few people have got confused about the bronze, silver, gold requirements. So I'll just reiterate them here. Bronze, solve this in any language this year, and you'll get the bronze badge. Solve in any 3 languages this year, 2024, and you'll get the silver badge. And if you want the gold badge, you need to have got the silver badge, so solved it in any 3 languages this year. And then you also need to have solved it in the 3 featured tracks, either this year or sometime in the past is okay as well. Featured tracks, Erik?
Yeah, there are JavaScript, NIM, and C++.
Okay, so you do get to play with some lower level stuff with C++ as well. I hope that's been fun. Again, please leave comments. Tell us which is your favorite. Tell us anything that we can do better for these videos in future ones. Thank you for watching. Thank you, Erik, and see you all soon. Bye for now.